Okay. Okay. Thank you, Zhi, for help me connect with the conference. And hello, everyone. This is Qidong from Xian University and the City University of Hong Kong. Here, I'm glad to introduce our work of when MOE meets LLMs, parameter-efficient fine-tuning for multitask medical applications. This is the outline of my presentation. I will first talk about the background and the motivation of our work. And then the proposed framework and experiments will be detailed. Medical is one of the most important domains for the application of large language models. It can benefit both patients and doctors. For patients, it can provide convenient access to medical knowledge. For doctors, it can assist for clinical decisions as the red figure shows, which can thus relieve doctors' workloads. Currently, there are two possible ways to utilize LLMs for medical applications. One is to adopt in-context learning to activate the general purpose LLMs. We can see the red figure. The core is to design the related prompts. However, it often faces the challenge of lack of medical domain knowledge. On the other hand, adoption of large LLMs such as MedPalm is a possible way, but it is closed source and with high inference costs, which is hard to be accepted by the medical institutions. And thus, fine-tuning open source LLMs with medical knowledge and clinical tasks seems a most suitable way. However, there are two challenges for fine-tuning medical LLMs. The first one is task variety problem. As the red figure shows, there are often several distinct medical tasks, such as CMEIE, which is a medical NER, and MedDG, which is a doctor dialogue task. Fine-tuning a single model for each task is laborious, while multitask fine-tuning on such unbalanced medical data is still underexplored for LLMs. And the other problem is high tuning costs. For the LLMs, it often needs prohibitive time and computational expenses for fully fine-tuning, which is impractical for medical applications. And therefore, we aim to explore a multitask parameter-efficient fine-tuning method in this paper. And next, I will refer to the method part. Generally, the input and output formats need to be modified for LLMs. Take the medical NER as an example. The traditional model outputs the entities directly from medical text. In contrast, the LLMs need an instruction template for guidance. Then, they output the textual answer and we need to extract the entities from it. As a result, the LLMs are fine-tuned by the pair of prompt texts and textual answer instead of the medical text and entities. Then, I'd like to give an overview of our method. As we know, the transformer layer is a basic unit in LLMs. We only accompany the dense K query and value with our MOE LoRa layer, and only a few parameters in MOE LoRa is trainable to achieve parameter-efficient fine-tuning. In specific, the MOE LoRa layer incorporates multiple shared experts to capture task-specific and task-shared knowledge across various medical tasks. As a general MOE, the weights for experts are important. We design the task-motivated gate function to determine the contribution weights of experts. It is worth noting that only one single gate for all MOE LoRa layers. Here, I'd like to introduce more details of the MOE LoRa layer. The basic structure is shown in the right figure. It consists of several experts, and each expert is a pair of low-rank metrics. And the forward process of LoRa is as this formula, which is the same for all tasks. Due to MOE structure, we can transform the process into this formula. For each task, it has distinct update weight Wg, and it is derived from the weights of expert EI and task-related experts with omega j. Then we can analyze the efficiency of MOE LoRa. Due to low rank characteristic, LoRa only needs to update R multiply D in plus D out. Since R is much smaller than D, the number of trainable parameters is fewer than W0. Here the W0 is the original width of the linear layers in LLMs. In MOE LoRa, the R-dimensional low-rank metrics are split into N experts. So the amount of parameters for each expert is as this formula in red circle. Finally, multiplying with N, MOE LoRa has the same number of trainable parameters as LoRa, which indicates high efficiency. As mentioned before, the expert weights are important for each task. We designed the task-motivated gate function for it, including a task embedding matrix and a linear transformation. A dense version is to use all experts directly by a soft mask layer. Then, inspired by some recent works using sparse MOE to elevate optimization difficulty, we also derive a sparse version gate, as this formula shows. After the fine-tuning, we can derive a unique set of parameters in LLMs for each task. This parameter recovery characteristic is vital for efficient inference as illustrated in LoRa. The formulas show the specific recovery process. The core is to combine the experts by task-related weights. At last, the fine-tuning process is shown in the algorithm. The vital steps are freezing pre-trained weights, sampling batch of data, and updating MOE LoRa and gates. In terms of inference, parameter recovery is the first. Then the LLMs can serve for each task by corresponding parameters. After the method, I will introduce the experimental results. In the experiments, we use a Chinese multitask medical dataset named Prompt C-Blue. Since the tasks are Chinese, we adopt ChatGLM6B as the foundation model. To verify the effectiveness of our method, we compare with 4 groups of baselines. The first group is LLMs without fine-tuning, which includes ChatGPT and Huato. Huato is one medical-specific LLM, and we choose the version of ChatGLM for fair comparison. As for LLMs with fine-tuning, we compare with p-tuning and LoRa. Then we find one model editing method can also be used in multitask fine-tuning, which is task arithmetic. The last group is cross-task generalization, which aims to transfer the abilities on source tasks to target tasks. Micro-FE, macro-FE, and ROACH are used as evaluation metrics based on different tasks. The table shows the overall performance. The LLMs without a fine-tuning group lag behind the other groups. This highlights the importance of fine-tuning LLMs to combine medical knowledge. And then, LoRa4 and LoRa4 plus TP both utilize data from all tasks, which underperform our MOE LoRa. The comparison indicates the task variety problem. And LoRa single, which fine-tunes for individual tasks, is also inferior, highlighting the shared knowledge across different tasks. We also implement a task arithmetic based on LoRa, but it performs bad because it is designed for fully fine-tuning, which may be not suitable to parameter-efficient fine-tuning. And the two cross-task generalization baselines also underperform slightly. This reason lies in that they require a vast amount of task data, which conflicts with multitask setting. Then, MO LoRa can be considered as an input-related gate variant. The inferior performance shows that redundant parameters causes the difficulty in training. Besides, sparse gate can help elevate the optimization interference and thus perform better on some tasks, but lose the shared knowledge by utilizing all experts. Next, we also conduct an ablation study. We found that removing MOE structure or task-motivated gate will cause performance drops, which indicates the effectiveness of both designs. To elevate the effectiveness of a single gate, we also implement multiple gate variants. The results illustrate the over-parameterization problem. Also, we experiment only inputting MOE LoRa or LoRa modules to attention layers. The similar performance comparison shows the robustness of our MOE LoRa. In terms of training efficiency, MOE LoRa has similar amounts of trainable parameters as LoRa. MO LoRa and MOE LoRa M are inefficient due to the extra gates for each trainable low-rank layer. And for inference efficiency, our MOE LoRa achieves the same latency as LoRa because of its parameter recovery characteristic. And finally, I will conclude our work. We first take the step to explore the multitask parameter-efficient fine-tuning for the LLM-driven medical applications, and then to satisfy the requirements of efficiency and effectiveness, we propose a novel multitask fine-tuning framework, and by the comprehensive experiments, we verify the effectiveness of the proposed MOE LoRa, and we have released the code of MOE LoRa, which has gained more than 100 stars. If you have any questions in implementation, you can also raise the issue in this repo. And the other two QR codes are the homepage of my research group and me. Welcome to give attention to us. And that's all of my talk. If you have any questions, please feel free to ask or email to me. Thank you.